I promise. I promise. Okay, let's get started. I've had a little bit of a full morning today, so I haven't had a chance to see if homework 2.3 is graded, but the solution should be turned on. And then 2.4 is due today. I did have one question about 2.4 via email, which I thought was maybe worth discussing a little bit in class. So the question was, if you have a channel, a C shape, do you convert it to equivalent angles for computing Y bar? And the answer is yes, if the flanges are connected, right? So if you had a C shape that was connected by the flanges, what you would do is cut it in half and determine the centroid of that upper angle portion. But I'll level with you, in practice, it is very rare that a C shape is connected in that fashion. But if it were, that's how you would do it. So I don't think I've ever encountered that in the real world, simply because if you look at the proportions of a channel, it's just a lot easier to bolt it through the web than it is through the flanges. That's not to say it's impossible. But that was a really good question, so I thought I would mention that, because I was like, okay. Any other questions? How did that last homework go? Was it all right?
Oh, yeah.
So I gotta believe that that last homework was culminative of a lot of other stuff that we've done. There really shouldn't have been a lot of new stuff on that last homework assignment, but it was just maybe a little longer since it was a lot of the other pieces that have been put together. So what we're gonna do today is another problem. I would say, I don't want to say just like it. The goal is the same. To take a tension member, evaluate its capacity, etc. But the tension member is different. So instead of dealing with a W shape, we're going to deal with an angle. It's going to have stagger. It's going to have odd stagger, and the way that we deal with that stagger is going to be a little unique. So there is going to be some differences. But I think that this is important to make sure that we are comfortable with this process. Okay, I think this is important. Okay. So I will go through the slides somewhat expeditiously because we've seen a lot of this before. It's just a new problem. So basically this is just our second tension member analysis example. So let's just make sure that we're all on the same page. So first off, we're all aware that our primary mode of operation is LRFD, load and resistance factor design. So we are factoring both the loads and the resistances independently based on their inherent uncertainty. And to ensure a uniform level of safety. It's why the it's why the resistance factor for yielding is higher than the resistance factor for fracture. It's why we use a 0.9 for yielding and a 0.75 for fracture. If remember, yields, yes, sucks, but all it really means is it's getting longer, permanently elongating. But if it fractures, snap it in half, and that's kind of a problem. So that's why that resistance factor is a little lower. But yeah, in the resistance side, we compute a nominal resistance, and then we adjust it by an appropriate resistance factor to yield a factored resistance. And then with the loads, we take those service loads. There's that new term, service loads. Service loads are unfactored loads. And we combine those using statistically calibrated load combinations to yield a factored load. Here are our 7 statistically calibrated load combinations. For those load combos, really the first 2 are the most common. And if we're being frank, really the first or the second one is the one that we end up using the most. The first one, it can control in the real world. Usually that's during construction when the amount of live load is very minimal. Okay, here are our 2 limit states, and we got a real introduction to those last time. I mean, we talked about them, but last time we really started to use them. And so what we found, and I think the last lecture really put this together, was that what we've been talking about up until now are just these pieces, like net area and U and whatnot. But these are our factored resistances. This is the expression for gross section yielding. So we take the gross area and limit it to Fy, and then adjust it by a factor of 0.9. Then net section fracture. We take the effective net area. The effective net area is the net area adjusted by U. We then limit that to the ultimate tensile stress and adjust it by a resistance factor of 0.75. And that's our net section fracture limit state. So for each of those pieces, we get Fy and Fu from table 2-4 for rolled shapes and table 2-5 for plates. Remember, there's a range for some of those values, and whenever there's a range, like right here between 65 and 100, which value do you use? The lowest, right? That's the conservative approach. They tell you the range to indicate the variability or the potential variability and ductility of the material indicated. Our complete expression for the net area for a bolted connection is to take that gross area, subtract the area lost due to the presence of bolts, which is the effective diameter of the holes times the associated thickness. And the effective diameter is the diameter of a bolt plus 1/8 of an inch. But then we need to add any necessary stagger factors to account for diagonal failure paths. And the stagger factor is S squared T over 4G, S being the longitudinal spacing and G being the transverse spacing. And that's our complete expression for bolted connections. For welded connections, the net area and the gross area are the same thing, at least for most fillet welded connections, because you're not removing any material. And just so you are aware, when we get into welds, 90% of the welds that we as structural engineers design are fillet welds. The other are groove welds, and to kind of be frank, we don't really do a lot of hardcore design of groove welds, but we'll talk about that when we get into it. Because groove welds are really a lot more of a specification thing than an actual design thing. But we'll talk about that later. All right, shear life factors. Shear life factors, these are the empirical expressions that tell us how much of the net area is effective in transferring stress due to those stress discontinuities that you get in the connection region. Remember, when you look at the stress field at the connection, it's just wonky, it's just weird. We don't get the luxury of avoiding that, though, when we're looking at fracture along the net section. We have to consider it. That's where these lovely empirical expressions come into play. It's possible that multiple cases can apply to a given connection, so you just have to go through and find which ones apply and go through it accordingly. This is one of those tables that's probably worth bookkeeping. Okay, so far so good? All right, this is the example that we're doing today. And I want to take a second and explain this member. I have found that in this class, what you want to do is make sure that you're seeing the big picture completely. Okay, so let's talk about this. I have an L5 by 5 by 1/2 of A36 steel shown in the figure below. I just realized that there's a slight error of omission because I need to indicate that the bolts are 3/4 inches in diameter. So I will fix that and re-upload. But yeah, we have 3/4 inch diameter bolts, and we've got stagger. We've got bolts that are staggered apart. And so what might be a little confusing is what's going on with this schematic versus this one, okay? And the easiest way to explain this is I kind of want to pull something up. So this computer does not have Autodesk Inventor on it, so I'm actually remote connecting to my computer in my office. But this is Autodesk Inventor, and so I've drawn a 3-dimensional rendering of the angle in question, okay? And let me scroll over here a little bit. This is the angle in question, okay? So if you kind of see, does everybody kind of see what's going on here? So we have one leg that has 3 bolts and then 2 bolts, and then we have 3 bolts here on this other leg, okay? So what's going to get kind of strange is our net area paths, okay? So if we look at our net area paths, we can samurai sword or lightsaber through the angle, and what we're going to see is that there's going to be 2 potential net area paths. The first is going to go like this, right? And so it's going to be the gross area minus how many bolt holes if I'm cutting through this path right here. 2. 2, okay? But another potential failure path, because remember, these are the lead line of bolts right here, is a path that looks like this. We go down, over, down, right? And so that path is going to be the gross area minus how many bolts? 3. But then we're going to have to add how many stagger factors? 2. The problem with one of those stagger factors is that here's 1, right? And so we just need the S and G for this path right here. But then what about this one? This stagger path actually crosses and jumps along from one leg to another, right? Okay, so that's going to be a little difficult to deal with without a little bit of a trick, okay? So here's the trick that we're going to do, okay? So the trick that we're going to do is this. All right, so I have an angle like this, okay? And I've got bolts here, bolts here, bolts here. What I'm going to do is I'm going to take a samurai sword or a lightsaber if I happen to be a sci-fi fan that day, and I'm going to cut through the angle right here, okay? And so what I'm going to be left with is a plate that looks like this with bolt, bolt, and then I'm going to be left with another little plate that's sticking out over here in space, right? Got a bolt right here, and here's where I chopped it off, right? So this is me, samurai sword or lightsaber. And then what I'm going to do is I'm going to take this little stub of a plate and I'm going to stick it up top right there. So I'm ultimately going to be left with a connection that looks like this. So basically what I'm going to be doing is I'm taking the angle and I am converting it to an equivalent plate that looks like that, okay? So you can see this is where I samurai sworded or lightsabered and stuck that in up top, so I've got these two here, that there. Now, what's left to do is to figure out the dimensions of this plate, and we'll talk about that here in a bit, okay? So notice how this schematic, I've left the dimensions off. We will get to that, okay? So far, so good? Okay. So bear with me, we will get there, okay? But before we get there, you all know by now that steel design is a science that involves a lot of lookups. So let's start off with the simple stuff. Start off with A36 steel. Got to break out your AISC 15th edition steel construction manual. Go to table what? 2-4 on page 2-48. We got to look up the FY and the FU for steel that's grade 36. I do want to, after we look this up, I do kind of want to mention something that I will bring up here in a second. But let's go ahead and do this first. So this is table 2-4. What is FY?
36.
36 KSI. And FU.
58 KSI.
Okay. One thing I'll mention, and I haven't really talked about this, and in most cases this won't be a problem, but if you notice in the manual the grid next to all of the steel grades with the white, gray, and black squares, the black squares correspond to preferred material specifications, right? So what is the preferred material specification for a W shape, as an example?
A992.
A992. Okay, A992 is the most common grade of structural steel that you will find W shapes in. The point I'm making is there may be a problem where I just say pick a W shape, and maybe I don't give you the material grade. That is a very good assumption for what the material grade could be, okay? chances are if I go to a service center or go to a mill and I'm looking for W24x76s, unless I ask for something specific, it's going to come in grade 8992, bless you. That's not to say that W shapes aren't available in other grades. Of course they are. Every one of those gray cells are grades that you can find W shapes in. And there are good reasons for wanting W shapes in different grades. A good example is if you're designing a steel structure out in California, and you've got really high load demands, really high seismicity demands. Maybe you need to bump up your grade of steel to be able to use a section that's reasonable for your project. But in most cases, you can go with an A992 grade. A good example, how many of you driven by the Innovation Building on 4th Avenue? I guarantee you those are A992, guaranteed. Because we aren't going to have to worry about that here. It's not a very large structure. I mean, it's not 30 stories tall. A992 grade for those W shapes any day of the week, and twice on Sunday, I guarantee you. Make sense? So if I don't tell you the grade, the point I'm making is if I don't tell you the grade, those black squares are a good way of denoting that, at least to get started. In most cases, I will tell you the grade though. Okay. All right. Let's look up some properties for this angle. All right, so let's look up some properties for the angle. Now,
Question.
yes, sir, yes.
One would be an example of a situation where 80 KSI would be used to give you.
80 KSI? So I can think of two really good examples. First off, for beams in buildings, probably not, except for if they're in their lateral system for earthquakes. So probably not. When would a grade of steel be that useful in building design? A good example would be columns in really tall buildings, okay? Because think about it, if you have a building that's 30, 40, 50 stories tall, that's a lot of force that column has to withstand. So think about it like this, if you're using a 50 KSI grade of steel, that's a really big column, right? Maybe you can make that column actually physically smaller by using a steel that can withstand more stress. Okay, so that's a good example of using that grade of steel in building design. Maybe for beams and moment frames, but gravity loads under really, really heavy loads, that would be a good example. For bridges, we do see the potential of using higher grades of steel in bridge girders. Most bridge steels that you're going to see used in the real world are also 50 KSI. Every now and then you will see 70 KSI. It's not common to see 100 KSI, but there are a couple bridges out there that do, I mean, very rarely. I haven't seen very many bridges, at least in our neck of the woods, that use 80. You might find that out west for some really, really long spans. But 50 and 70 are probably the most common that you would see in bridge steels. But yeah, the most direct application I can think of for something that high is columns in really, really tall buildings.
So then in a design, if there was a need for a higher strength, then you would use a higher number?
Yes, so here's a good example of where that would happen in the real world, okay? So let's say you're the structural engineer on a new building in Denver that's going to be 60 stories tall, right? And you say, well, I'm just going to use 50 grade normal steel, right? And you do the math, and you find these columns are huge, right? The architect comes back and says, those columns are too big. And you as a structural engineer go, well, I'll just use more of them. I'll space them closer together so that each column is responsible for less load. Then the architect comes back and says, well, that ain't going to work either because I need open space. Well, there's this thing called physics. How am I going to get around it? Well, maybe use a stronger steel. So that's a really good question. And that's good. I love that stuff. That's great. Because other than that, there's not really a lot you can do, you know. And going with something with concrete, the columns are just going to get even bigger. So, sound good?
Yes, thank you.
All right. No, this is great stuff. Okay, now let's talk about the angle. Okay, I'm asking, so for the angle, we have an L 5 by 5 by 1/2. Last time I said I want the area, the flange thickness, the BF, the D, and all that. I want you to tell me what properties you think we need from the angle for this problem? Like, for the steel, we knew we needed Fy and Fu. What properties are we going to need for this angle to do this problem? I'm asking you. Somebody shout out one.
R is here.
Okay, hold on. I'm going to get to R in a second, but I heard somebody else say something. What was that?
Gross area.
The gross area. We're going to need the gross area. What is the gross area for this member? Okay. So we need 4.79 square inches. Now there is a property that you're not necessarily going to look up, but we're obviously going to need to compute net area.
Bolt, right? The effective bolt
Well, we can get that from the bolts. I'm talking about
from the.
what else do you need to compute a hole diameter or a hole area? The thickness, right? There's nothing to look up though. What is the thickness? It's a ½ inch. For angles, the thickness is just what it's listed. So we need the thickness, right? Now, somebody else called something out. They said the R value. Why? Why'd you ask for the R value? Did it ask?
No.
So let me ask you a question. If we look up the R value, what could we do with it? Because we can't determine whether or not the member meets slenderness limitations. We don't know how long it is. But we could, on the flip side, say, well, here's the maximum length the member could be under slenderness limitations, right? That's something we can do. We can't just check it for slenderness. We don't know how long it is. Does that make sense?
Yes.
So let's just go ahead and write it down for the heck of it, but know that the problem didn't actually ask us to do slenderness. So now, which R value do we use?
Smallest.
All right, which one's the smallest?
Z.
Z. Anything that doesn't have an X or Y axis symmetry will have an RZ value. What is RZ for an L5 by 5 by half?
0.98.
All right. Is there anything else you think we ought to look up? Okay. Now, let's talk about X bar. First off, what's the difference between X bar and Y bar for this shape? Well, you're right, there's two of them, but what are they?
Would they be the same?
They're the same.
Yeah.
They're the exact same because it's an L 5 by 5 by 1/2. The distance from here to the centroid and the distance from here to the centroid are the same. You don't have to believe me. Look at the table. They're the same. Now, let's just go ahead and ask, what are those? So we'll say X bar equals Y bar equals
1.42.
1.42. All I'm going to say is I want you to remember this moment a little later in the problem when we talk about X bar and Y bar. Because how we use those is going to be a little unique. We'll get there. Okay. Is this not working? Okay, so like last time, we were able to go ahead and do gross section yielding. Let's go ahead and do that. Okay, so So 0.9 FYAG, 0.9 times 36 KSI times 4.79 inches squared. VPN equals what? you gotta break up your Casio FX 115 ES Plus or similar scientific count. Man, I'm putting y'all to work this morning.
155.1.
Yeah, when you get to the final limit state, it is perfectly fine to just say, let's just go 1 decimal place. So this is the gross section yielding limit state, right? So, in order to determine the capacity of this member, that's one limit state. What do I now have to do? I now have to assess the other limit state, right? So I got to calculate the net area, I got to calculate the shear life factor, I got to calculate the net section fracture limit state, and then I got to take the smaller of those two, right? I certainly wouldn't be the type to make you do all that and then find that this one's the smaller one, right? I would never do that to you.
Huh,
You would do that.
interesting.
I run.
Very, very interesting statement.
Let's see what happens. I don't actually remember, but I know I've done that before on a couple problems, so. All right. Net area. Okay. Now, before we look at this net area, we've got to use a little bit of our noggins first. Okay. What is that dimension right there? I know that's simple. Just trust me. You'll see what I'm doing here. What is that dimension? 5 inches. Okay. So, here's my second question. What is that dimension? 4.5 inches, right? Okay. Okay. All right. The point I'm making is this. So what we're going to be doing is we're going to be converting this into an equivalent plate. And I think that initially your first thought is to say, well, it's a 5 by 5, right? So that means this is 10 inches, right? No, it's not. You're double counting the thickness. It's 9.5 inches, okay? Does that make sense? So what we're doing is we're taking, this is 5, 4.5 on top of it makes 9.5 inches. Is that okay? All right, I just wanted to make sure that was clear, right? So what I'm getting at is that this dimension here is 5 inches. This one is 4.5. Okay, just be consistent on your dimensions. It's really easy to think that's 10. That's not 10. Okay. Now, what we've got here is, so from our schematic up here, so I'm just sort of repeating this one. We've got 1, 2, 3, and then we've got 1, 2, 1, 2, 3. And what we need to start doing is figuring out some dimensions for this, okay? Now, if you look at the top part here, this gauge spacing is 1.5 inches, okay? So what I'll do is I'll say this, 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 this. These dimensions right here are 1.5 inches. Okay. Now let's see if we can figure some stuff out, because we're going to have to figure out this and that. That's sort of our key distance that we need to figure out. Now, do we know this distance right here? Sorry, I misspoke. This lower spacing down here, these are the S values. Do we know this distance right here?
1.5.
1.5 inches. Okay, that was given to us at the very beginning of the problem. Okay. Now, what about this one? Let's see what we can see. Let's go up here. Okay. So, let me scroll up here a little bit. Let's write on this. Okay. So this dimension is 1.5 inches.
4.5.
Sorry, what?
4.5.
You mean for this value right here?
Yeah.
You're right. You are right. It is 4.5 inches. That's really good. Now, let me show you how you can reason through it if you're having a hard time seeing it. Okay. So what you can do is you can recognize this dimension is 3 inches. So if this is 3, that's 2, right? So we know that this dimension right here is 2 inches. And this dimension right here, right? If that's 2 and that's 1.5, that's 3.5, that makes this 1.5. That's this dimension right here. So if this is 1.5, that's 1.5, that's 2, the whole thing is 9.5, just subtract it out and you get 4.5 inches. Does that make sense? Is everybody okay with that? This is good stuff. I really like this. So this dimension right here is 4.5 inches. I'm going to redo that. All right, is everybody okay with this so far about how we came up with these dimensions? Does that make sense? Okay, all right. Now, let me put some labels on this so that we're all kind of speaking the same language. Okay? I'm going to call this G1, and I'm going to call that G2. And I'm going to call this the spacing, right? Because we're yanking on this thing left and right. So the gauge spacing is perpendicular to the loading. The longitudinal spacing is parallel to the loading. So let's write down some values over here. So we have S is 1.5 inches. We have G1 is 4.5 inches. We have G2, 1.5 inches. We know the thickness is 1/2 inch. Now what else do we know? We know the bolt diameter is 3/4. So what does that mean about the hole diameter? 7/8. Boom. Now, if we start identifying our net area paths, how many potential paths do we have? 2. So, and just to keep things simple with all the letters and whatnot, I'm just going to say that's net area path 1, like that. And net area path 2 goes like that. Is that a fair statement? Okay. So I think that makes the math a little easy. So net area 1. So tell me what to do. How do I compute the net area of path 1? Somebody tell me. I take the gross area and I do what?
Subtract 2 bolt holes.
Subtract 2 bolt holes. So the gross area minus 2 DET, right? Which is 7, wait, is that, did I get that right? Yeah, or no, 4.79. 4.79 minus 2 7/8, 1/2. And so what do we get for that? We'll say 3 decimal places if we can, just to make sure we're all getting the same answer. 3.915. Do I have a second on that? Okay, now, so help me out with net area 2. We take the gross area minus how many bolt holes? 3. Now, how many stagger factors do we add? 2 different ones. But are they the same? No. All right. So what we'll say is 3 plus s squared t over 4g1 plus s squared t over 4g2. They're different stagger factors because they're different diagonal paths. See, this is one of the reasons why we had that homework assignment that had like 11 different paths, because I wanted you to be able to identify them in cases where there actually are different paths and different staggers and whatnot. It's a perfect example of one where you kind of need to make sure that you're paying attention and checking the right ones. All right, so now what we'll do is we'll check this out. So there's that, then plus 1 stagger factor. Make sure and square your s's. Don't forget the 4 on the bottom. And so when we check that out, what do we get? We'll say 3 decimal places on this one too.
0.728.
3.728?
Yep.
I heard a second on that, so we can go with that. All right. So we have this net area and this net area. Which net area do we use? The smaller one, right? Because these are referencing capacity, right? So worst case scenario is the one that's going to fail first, the one with the smaller area. So therefore, the net area is 3.73 inches squared. And we'll say rounded to 2 decimal places there. So far, so good? All right, any questions so far? So, what do I do next?
Shear life factor.
Shear life factor, okay, shear life factor. So next comes, so here, let's divvy this up a little bit so that it's a little easier to kind of see what we did. Which cases apply to this member? Hold on. Hold on about that. Let me hold. Let's pull this back up again. What's the difference between case 1 and case 2?
All elements all connected.
Versus some of the elements. Could somebody tell me Does case 1 apply to this move?
I say, yeah.
I say yes too. This cross-sectional element only has 2 legs, this leg and this leg. Both of those elements are connected by fasteners or welds. I propose to you U is 1. Remember that X bar and Y bar that we spent so much time looking at? Are we actually going to use them?
Apparently not.
No, we're not. And I want to be clear. I think it's okay to look up values in steel design and not use them. Sometimes it's a little better to do that than it is to start the problem and then realize, oh, I forgot this and look it up. Oh, I forgot this and look it up. Just look up all that you think that you need. If you don't use them, it's okay, right? That's fine. So the shear lag factor for this one is 1. It would not be 1 if only one of those legs was connected. Then we'd have to do 1 minus X bar over L and look at case 2 versus case 8. But all of the elements are connected by fasteners or welds. So what I'll do is I'll separate that one too so that you kind of see when we follow what we did. So now we're able to do net section fracture. Okay, and for net section fracture, the limit state is BPN is 0.75 FU ANU, which is 0.75 58 KSI 3.73, and then a shear lag factor of 1. And so what do we get for net section fracture?
$162.2.
162.2. Do I have a second on that?
Yeah.
So, to summarize, for gross section yielding, we got 155.2 kips. And for net section fracture, we got 162.2 kips. So it looks like we did all of that for nothing. And that was our answer all along. The honest truth of it is, that might happen, it might not. There's just so much variability in the shapes that we pick, the thicknesses, the cases of shear lag factor. You have real, I don't know anybody that can actually just look at a shape and say, yeah, gross section yielding is going to govern, or yeah, net section fracture is going to govern. I mean, and let's not forget that later on we're going to do block shear, and block shear is different. And so there's going to be a third one in there, and that one really, I mean, the math that goes into that one, just, there's no real way to predict it. So the short answer is you just kind of have to do both and see which one governs, okay? All right. Now, if you would like, I'd like to give you a small taste of design before we call it for today. And then next week, we will actually start some steel design. This whole time, we haven't actually designed anything. Let's talk about design a little bit. But before I end this, does anybody have any questions? Let's talk about steel design. So, just to give you a taste, this is not going to be required for your homework assignment. This is not going to be anything that you need to know for between now and next week. I just want to give you kind of a taste of it. Okay, so we've got our limit states, we've got our tension member limit states, etc. Let's talk a little bit about design, okay? And I want to show you how we do this, okay? Some of this is mechanistic and derivable. Some of it is rule of thumb, okay? And let's just sort of think about it. I think we're in a good headspace right now before we end today to think about this, because we just did a tension member problem. So some ground rules for design, okay? So we covered tension member analysis, and tension member analysis, is if I give you the details of a tension member, which I have done in problems like this, I say, tell me about the member's performance. That's what I mean in this class when I say tension member analysis. Now let's discuss tension member design. Tension member design would be things like, given some constraints or some loads, select the lightest member. That's what I mean by design. Now before we begin, I want to establish some ground rules. In this class, we will always strive to select the lightest shape possible. Now if I'm talking about W10s, how do I know which one's the lightest shape? The second number, right? The second number tells you how heavy it is. The smaller that number, the lightest shape. Why would I care about the lightest shape? Well, if I'm paying for steel per pound, less steel means less money, right? So we are always going to select the lightest shape possible. And in this class, I will always design the problems so that they have some constraints that we arrive at the same answer, okay? That doesn't mean that will always happen in the real world, but I'm doing that just so that we all get at the same answer. So I might say things like select the lightest W12 or select the lightest channel, when in the real world, you might be able to select whatever you want, you know? But I'm doing that so that we all get to the same conclusion at the end of the problem. Now let me show you how we can go about design pretty easily. So let's say we're talking about gross section yielding. Let's just live in a world where all we cared about was gross section yielding. We don't care about any other limit state. All we have to do is select a member that meets gross section yielding limit state. Well, we're talking about LRFD, right? So what does LRFD say for gross section yielding? Let's pay attention to this box right here. What it says is that the resistance has to be greater than or equal to the loads. What are the loads? Well, the loads are 1.2 dead plus 1.6 live, whatever the load factors are, right? What is the resistance? 0.9 FYAG. Now, if I'm in design mode, what do I not know about this box? AG. I don't know what the area is. So solve for the area. And I propose that under this limit state, the area needs to be at least PU over 0.9 FY. So solve for what I'm calling gross area design. Pick a member that has an area at least that or bigger. Boom. What about slenderness? Slenderness says that the slenderness has to be less than or equal to 300. If I'm in design mode, what do I not know about the member? Well, let's talk about that. If I was designing a tension member in a truss, I know how long it is, but I don't know what the member is. And if I don't know what the member is, what do I not know about that member? R. So solve. Find a member that has a radius of gyration of at least L over 300. Make sense? Now here's where things get weird. What about net section fracture? How do I compute the net section fracture limit state? Well, I've got the gross area. I then take that gross area, convert it to a net area by subtracting the area loss due to the presence of bolt holes. And then I take that net area and I reduce it based on some shear lag factor. But if I'm in design mode, I have no idea what the member looks like. No clue. So I don't know what the thickness of the member is. So if I don't know what the thickness, I can't derive some expression for net area. And if I don't know what the member looks like, I can't find a connection eccentricity or any of that. So I'm going to have to just guess something. So I propose that the effective net area for the purposes of design is about 75% of the gross area. So this is going from gross area to net area to effective net area. So I propose that the net area times U is about 75% of the gross area. That is a shot in the dark. That is a total guess, okay? But we're going to use that as a means of selecting a member. But the member that we select is going to be a trial member. It's going to be a guess. We are then going to have to take that member and analyze it. It might work. It might not. Okay? And that's where the iterative process of design comes into play. but at least this will give us a good shot at getting our most economical selection first, okay? There is only a discrete number of shapes in the manual, so we have to just have a way to find the best one to start with. So what we end up doing is we end up saying, okay, here's gross area or gross section yielding limit state. Here's our net section fracture limit state. The reason why there's a 0.75 squared is because one of them comes from taking this and converting it to that. The other comes from our resistance factor. And so I propose we start looking up shapes that meet this. Either the load divided by either 0.9 Fy or 0.75 squared times this, whichever one's smaller, because that'll give us the biggest area from which we select a trial shape. And then we take that trial shape and we analyze it. But how do you design a tension member? We'll talk about this on Monday. Get your factored load. We compute what I'm calling our two design values. The design values being a limit on the radius of gyration and a limit on the gross area. Pick a member, take that member and analyze it and make sure that it works. Summarize the results and compute the efficiency of the design. We'll talk about the efficiency of the design on Monday, but by and large, as I mentioned, basically goes to a Price is Right analogy. So efficiency can't be over 1 because then you don't go to the showcase showdown. All right, that's all I got, everybody. I will see you all on Monday.
It's the box. That was a while.